Can you guys hear me? I can hear me. Sweet. All right. So it's true. We're going to continue the trend. This talk is not about Ruby at all. This talk is about space. Let's hear it for space. All right. All right, that's good. It's 4 o'clock on a Friday. There was no guarantee any of you would be awake. I love space. I love space exploration. I have my whole life. I know I got into a technical field because I love space and space exploration. I know a bunch of other people did. Raise your hand if you know you did. I'll bet a lot of people did. Exactly. I mean, there's just so much that's really, really inspiring. And if there's one thing above all else that inspires so many people, it's the Apollo program, right? I mean, we landed on the moon. How cool is that? And there are just so many things that you can be inspired by. I mean, there's the Saturn V rocket that has millions of pounds of thrust and shoots fire a quarter mile out from its engines as it's going into space, right? That's awesome. There's awesome math for like orbital mechanics and stuff, right? Electrical engineers built awesome hardware to make everything actually work. Astronauts were like the best pilots at the time, right? They were test pilots for crazy stuff like the X-15. And then they went into space, and they were brave, and it was awesome. And then you hear things like, oh, yeah, and we landed on the moon with less computing power than is in, like, my watch. And that sucks. I mean, we're software developers. We want to hear awesome stuff about software, but no one ever talks about software in the Apollo program. And so for a long time, I figured, okay, maybe there really wasn't much. Maybe they had some computer in the Apollo capsule, and it was just a bunch of circuits, and maybe it was smaller than anything else that came before it, and, it probably wasn't pretty, and it probably wasn't programmable, but that's all wrong. There was an incredible amount of software development effort that went into the Apollo guidance computer, and it is just awesome. So that's what it looked like. It's not very pretty, and it's not very fast. It is true. A double precision floating point multiply took 1 millisecond. I did some rough math. My little computer over there, compared to the Apollo guidance computer, it could do all of the computation done in all the Apollo missions ever in 1 second. But I'm not even sure that thing is going to last through this talk. Whereas in all the Apollo missions, the Apollo guidance computer never once failed. It hit some known bugs. They had to do some crazy workarounds, but there was never once any sort of failure. And that's pretty awesome. Let's see, what was I going to say next? What's even more amazing is that it's not just a bunch of little circuits that are pre-programmed. It's if you look at the hardware, it's a general-purpose computer, pretty much exactly like any computer we have today, right? It has an instruction set that's really familiar. It has RAM. It has some read-only memory. Programming it was pretty much similar to writing assembly today. And what's even crazier is that they built all this in the 60s. Now, to give you an idea of what this means, the project was started in 1961. In 1950, software was mentioned in a paper for the first time, the word software. So before 1950, they had written software, but they didn't really realize that this software thing was going to be different than just building a computer. So Firefox is 11 years old. When they started building the Apollo guidance computer, software was as old as Firefox. Just think about that. In 1965, they were about halfway through building the Apollo guidance computer, and the MIT Instrumentation Lab, that's the guys that built it, they got this brand new fancy computer to do all their work on the ground, and it was called an IBM System 360. Now, there's a certain famous person who worked on that project. Who knows who it is? That's right. What did he give us? And when did he write that? 1975. So by then, the Apollo program was all shut down. So all the software developers working on the Apollo guidance computer were contemporaries of Fred Brooks. They were learning exactly the same things. They're making all the same mistakes at the exact same time. In 1968, Apollo 8 was orbiting the moon with men on board, the Apollo guidance computer was essentially done, right? They had some work to do to finish up for the other missions, right? But the Apollo guidance computer was feature complete in 1968. In 1969, these two developers at this place called Bell Labs started working on this new programming language. It was called C, and they started working on this new operating system, and it was called UNIX. So the Apollo guidance computer was done before those even started. That's pretty crazy. So what do you learn when you build software in the 60s? I want to first ask you guys a question. Who has built some sort of web app or system or something that relied on someone else's system, right? Any sort of API or anything like that, and it was at scale? Pretty much everyone. Okay. And what happened to your system the first time their stuff broke? Everyone's laughing. Yes, someone made an explosion move. Exactly. And hopefully you got smart, and later on you were able to handle anything that this other system breaking could throw at you, right? And maybe your stuff didn't work that great, but at least it chugged along a little bit, and you didn't look so bad. Okay, let's now talk about the pivotal moment in the entire Apollo program, and that's obviously the first landing on the moon during Apollo 11. So they're in this guy. So Neil Armstrong and Buzz Aldrin are in here. It's the lunar module. They're orbiting the moon, and then they're starting the descent towards the surface of the moon. And the last couple of minutes of this, like the last 10 minutes or so, is something no one had ever done. They'd only gotten into a tight orbit around the moon for Apollo 10. This is by far the most workload-heavy part of the entire mission. Neil Armstrong said on a scale of 1 to 10 in terms of difficulty, he called it a 13. So these guys are focused, right? They're working hard. They're coming in. They're just a couple minutes from landing. And then on their little dashboard, a huge thing lights up. It says, like, master error, program alarm, something's wrong with the computer, oh no. And they're freaking out. They're distracted. They fly like 3 miles past their landing site into a field of craters, which is no good. Back in mission control, everyone is freaking out. They had never seen this particular error before in all the simulations they did. There happened to be a guy from MIT there who had been working on the Apollo guidance computer, and he had happened to have been told beforehand that he should write down a little cheat sheet of every single error code that can be displayed and what you should do, which is an extremely smart idea. And he looked up the error code that they had never seen before, and his note said, as long as nothing else looks wrong, then you're still go. So he told everyone, okay, we're still go for landing. And he actually got a medal from the president for saying that. Okay, and then we all know, obviously, they landed on the moon. So what happened where there was this program alarm that said the computer was doing something wrong? So in 2014, if you write some code that does an infinite loop or something, it uses way too much CPU in your computer will generally not crash. Sometimes, but generally not. In the 1960s, it generally would. The idea that you could have one computer running multiple programs, interleaved to appear simultaneous, they call it time sharing, and it was first talked about in 1957. So the very idea that you could have multiple programs running at all together was extremely new. The Apollo guidance computer did this. I mean, there were programs to fire rockets, there were programs to fire thrusters, there were programs to take input from astronauts, to display stuff, to send data back to mission control, all sorts of stuff, and they were all different tasks. And now at the time, almost every single system that did this, just whatever program wanted to run, they give it a little slice of time and then move on to the next one, right? Very simple, very straightforward. They called it like static time sharing. Obviously, our computers don't do that today, right? We give everything a priority, and then some very smart and very sophisticated logic decides what we should run based on the highest priority stuff, right? The Apollo guidance computer did this too. And some engineers at the time hated this idea. They're like, you can't know what's running at any given time. It's hard to test. Well, so it turned out what was causing that program alarm, it was too much CPU usage. The Apollo guidance computer was working really hard during the landing too, right? It's calculating the trajectory to go in. It has to fire thrusters at exactly the right time. It's sending back data to mission control. And the engineers knew this. They calculated it all out. They said, yeah, during the landing there'll be peaks to about 93% CPU usage, but that's okay. We've got everything under control. There was some other hardware on the lunar module that was sending a bunch of extra signals to the guidance computer and causing it to use like an extra 10% CPU. So right, you can do the math, and that's no good. Of course, they were smart enough to give this stuff a really low priority. It was actually signals from like the rendezvous radar, which they didn't even use unless they were going to go back to the command module if they were aborting. And without that priority-based system, right, that was smart enough to say, here's the stuff that's really important that we need to run. If something else happens to be running that we don't expect, as long as it's lower priority, we'll just not run it, and everything will hopefully be fine. If they hadn't done that, they wouldn't have landed on the moon for Apollo 11. They would have had to abort. So the takeaway is, spend a little extra time, make your system handle failure gracefully. As a side note, if you handle something gracefully and then pop up a huge error that says program alarm and is super scary, you maybe could do a little better. Something like everything's okay, even though we're running a little low on free CPU. Okay, let's talk about something that hopefully we all love. Let's talk about testing. Yeah, testing. Obviously, lives were at stake in the Apollo program. They did a lot of testing. They did a lot of automated testing. They did a lot of unit testing. They even called it unit testing, but they called it unit testing with quotes because it was so new. They didn't really know if that was actually a thing. And the engineers, you know, they say, yeah, unit testing was great. It helped us. It was cool. But they don't love it. They didn't say it was like the reason we landed on the moon was because of unit testing. And I think the reason for this is pretty straightforward. Aja pointed out, when you write functional code, it's easy to test. Well, all the code for the Apollo guidance computer was functional, not in just the programming sense, but in the actual mathematical sense. It was all guidance equations, right, with inputs and outputs. It was easy to test. And furthermore, in the 1960s, the computer science degree did not exist. Everyone programming for the Apollo computer was trained in math or had learned enough math to essentially have a degree in math. And so when you put a bunch of mathematicians together and you tell them to code up a bunch of functions that they know really well, they can generally do it. They also did a lot of integration testing. And when you read what they talked about for integration testing, they loved it. They said it solved so many problems. It helped them so much. In 1972, MIT published essentially a retrospective of what happened during the software development for the Apollo guidance computer. And they listed two problems that they had for the entire project that just plagued them the whole project, and they didn't figure out how to solve. The first one was how to estimate schedules and how to meet them. Oh, and we have a little picture here, sorry. We have no idea how to solve that today. They had no idea how to solve that then. It's a hard problem. The other thing that they said was really hard is getting up-to-date specs and requirements of other systems, right? And that's hard. We have a problem with that today. But what they did discover is integration testing can help you figure out, at least when you have this wrong, right? When you write unit tests, it's generally all your code or someone on your team's code. But the whole nature of integration testing is it's someone else's code too, or their own hardware or something. So you put everything together, you put your whole system together, and you see what happens, right? And if your integration tests pass, you don't necessarily know anything, but if they fail, you know you did something wrong. And what you did wrong isn't necessarily that you coded something wrong. What you probably did is you made a beautiful implementation of the wrong thing. You coded up something that was great, it was perfect, except that you didn't know what to write. And so then you can actually go out, and there's no easy process for this, right, which is why it's still a problem today, but then you can go out and talk to the other people that you work with, right, the other parts of your system, and figure out which part either got something wrong or which part you got something wrong about. So it doesn't cure everything, but it helps. So it leads to a really interesting, something I hadn't heard before, a really interesting takeaway. So unit tests prove your code, and integration tests prove your communication. And we all know communication is maybe one of the hardest parts of software. Maybe the hardest, maybe even harder than writing the actual code. So that's pretty cool. Let's talk about their teams. This is after Apollo 13 landed and everyone was happy. So in 1961, the Polygons computer contract was signed. Didn't mention anything about software. They didn't know they were going to have to write any code. Pretty soon after that, they realized they would, and they settled into having about 20 software developers. And these 20 software developers had no managers, no deadlines, no requirements, very little communication with anyone else. And the reason is, we didn't know at all in 1961, we didn't know how we were going to get to the moon. We didn't know what, even at a high level, a spaceship that goes to the moon would look like. Would it be one big spaceship? Would it be two smaller spaceships? Would we send one giant rocket? Would we send two little ones and then build a spacecraft in space or something else? No one knew. No one knew if you could, with math, navigate yourself to the moon. Figured it could be done, but we didn't actually know how. And no one knew, even if we had such math, could we build a computer to do it? So there was no point in setting a deadline. What you wanted to do was experiment and fool around and prove out all these concepts. A couple years later, we knew how we were going to get to the moon. We knew we were going to use two little ships. One would be specifically for landing on the moon. Turns out it's a lot more fuel efficient. We knew that with a little sextant, just like sailors in sailing across the Atlantic or the Pacific or whatever, you could look at the stars and the moon and angles and figure out where you are. And it was proven that you could use math and accelerometers and get yourself in extremely precise orbits around the moon without any help from anyone else. Pretty cool. And we knew that if you use these new things called integrated circuits, you could build a computer that could do all that math for you in such a way that it would actually all work. So now, around this time, there are 400 software developers. And they had lots of managers. They had lots of deadlines. They had lots of communication. And the reason is they were really focused on getting specific things done, right? JFK said, we got to be on the moon by 1970, so they had a pretty harsh deadline right there. Last year, if you were here, Sarah talked about open and closed modes of thought, right? Is that right, Sarah? In open mode, you're open to new ideas, right? You're exploring, and then in closed mode, you're working to getting specific things done. Did I butcher your talk, or is that about it? There you go. She agrees. That maps perfectly to these two team sizes, right? Early on, you're just trying to see what can work, and later on, you're trying to get shit done. So it sort of goes without saying, make sure whatever team size you're on is set up for doing the thing that you need to do right now, right? No startups start with 400 people. At least they don't last very long if they do. And likewise, we'd all be pretty nervous if we found out that like the Google search team had 20 people. That would not be cool. A side learning from this is switching between the small, scrappy team to the big, like process-oriented one is really painful. NASA complained like crazy when there was a really small team. They said, you guys got to get your shit together, you got to get organized. When they did get bigger, a lot of the engineers left. They said, we like exploring new things, we like fooling around, we like not having managers. After Apollo 8, a good number of the engineers actually left, and they went on to the next thing. But the point is, we wouldn't have landed on the moon with 20 software developers the whole way through, and we probably wouldn't have landed on the moon with 400 software developers the whole way through. So make sure your team is the right size. Let's talk about working with users. I take that back. Let's talk about working with astronauts. Who's seen The Right Stuff or read the book? Great movie, great book. How does it describe the astronauts? Okay, goofballs. Cowboys, right? So they are super confident, super arrogant, super hard to work with. They're just like software developers. So we all know a few things about working with users, and there's one thing that really stuck out to me that they learned really quickly, and that's astronauts, just like any other users, don't know what they want. There's a great story that illustrates this. The Apollo guidance computer was also an autopilot, right? You could set it to navigate the craft around pretty much everything except the actual landing on the moon. That had to be done by a man because you got to avoid boulders and stuff. You could probably do it now. So the Apollo guidance people said, hey, astronauts, we can build you this autopilot that'll do the reentry at the end of your mission for you, right? You just press some buttons, sit back, and we'll get you through, the atmosphere. It's a tense moment, right? Because if you come in too fast, you burn up. If you don't come in steep enough, you fly back out into space. It's no good, but a computer can handle that pretty well. It turns out the astronauts had trained to do this, and they said, no, there is no way some computer is going to do this for us. The astronauts were really just trustful of all forms of automation, computing, even digital, analog, whatever. A lot of them had their friends who had been killed in accidents in the 50s and 60s and things like the X-15, so sort of reasonable. But they said, no, we promise, every single one of us, guaranteed, will manually do the entire reentry. There is no way that we will let some automated system do this for us. They never, ever used the manual reentry. Every single mission, I take that back, the first mission, they tested manual entry for about a minute. It turns out when you've been in space in a little box for a week and a half, and there's 3 minutes of work that a computer can easily do for you between you and the warm Pacific Ocean and like real food and fresh air, you're going to just press the button and then sit back. So they learned that. Here's another interesting thing. Let's say you've built a computer that can navigate you to the moon, right? And let's say you've got astronauts that are going to be in the ship with you. How do they communicate with each other? Keep in mind, human-computer interaction as a field will not be invented until 1980. So you don't really know much about working with users. You can't use a CRT screen because they're too heavy. You can't use an LCD screen because they haven't been invented yet. And again, astronauts hate the very idea of automation. They just want a joystick that manually controls everything with actual cables, not even like fly-by-wire. So what do you build in that case? And I want to show you what they built. Thanks to the work of some other people, not me, who are very smart. They've built a JavaScript emulator of the entire Apollo guidance computer. And it's live demo time. Who's excited? Yeah. All right. So in all its glory, this is the interface to the Apollo guidance computer. So what you get are 3 lines of output. That's all the computer tells you about anything. You get this stuff up here that basically says what it's running. And now you can do something really cool. So how you communicate with this computer is you give it a verb and then a noun. So verbs are things like, show me some data. So verb 06 will show you some data, and then noun 65 is like the current system uptime. So hit that, and this thing's been running. You have to know, by the way, there's no decimal points, so you have to know what all these fields mean. They don't exactly get labels. So this system's been running for 0 hours, 20 minutes, and 2.57 seconds. Okay, let's run verb 16. This says, show me some data, and then keep updating it, and noun 65. And now it's the exact same thing, except every second it's updating. So you've got this very simple system that's still very powerful. Stuff can be entered in quickly, right? Astronauts are maybe under some time pressure sometimes to make sure that the spacecraft's doing the right thing. By the end of the Apollo program, the astronauts were so adept at this that the engineers were astounded. And that's because it gave you this really simple but powerful interface. Now, who here is reminded of something, a certain program that we might all use almost every day that has verbs and nouns and other things, and you can combine them in interesting ways? It's Vim! It's Vim! I have no idea at all if this influenced the design of VI or Vim. VI was made in the 70s, and then Vim, I think, in like the early 80s. But I just think that's really, really cool. Still, 40 years later, we're using essentially that same sort of concept that they came up with, right? And I use Vim every single day. I love me some Vim. And I know a lot of us do. So I just think that's awesome. You guys should definitely check this out. You can actually like simulate an entire launch, and it's awesome, but I don't have time to show it to you. Let's go back to the slides.
I can make my talk shorter if you want to do it.
So you can do like 5 seconds per slide instead of 10?
Sure.
All right, okay, let's try it. Okay, so there's a launch checklist. Let's open this thing up. Okay, I did these two. Okay, verb 37 says run a program, and then we want noun 01. That's like the pre-launch, like make sure everything looks okay program. Nope, didn't work. Let's reset. Verb 37, was it enter noun 01? Nope, all right, I have more. Okay, I have multiple copies of this for this reason. Verb 37, noun 01. I think it's supposed to flash for a second. Oh, it's supposed to be calibrating something. Maybe it's taking a second. Nope. It says, hold on, let's try. I have another one. Oh, I have another one in Chrome in case I close all of Firefox. Okay, it said verb 37, enter 01. Again, HCI hadn't been invented for another 20 years. There we go. So now it says program 1 is running. Yeah. And then this little thing, this guy over here is gonna calibrate any second now. There we go. So basically the guidance computer is figuring out where it is. And then as soon as this switches to 2, let's go back to our launch checklist. Major mode 2, the pre-launch thing will happen. Okay, we're in program 2. Now you hit the launch button. Bam! And now this thing says the Saturn first stage is firing. And now this thing switches to, I think this is velocity. One of these is altitude. Another one's like downrange distance. And they're going up, right? You can imagine that we're in a rocket and it's all rumbly and you're being pressed to your seat and stuff. It's not quite as dramatic, I guess, when it's just a couple lines of text. But you can fool around with this. It's still pretty cool. All right. Now we're really going back to the slides. But only to say, I'm Julian Simioni. I work at 42 Floors. You can tweet at me. You can read my blog when I update it. That's a picture of me. I'm a pilot. It's really fun. You should all get your pilot's license. All right. Well, thank you so much, guys. Cool.